This diagram shows a standard vector space, floating in an abstract void. We have a problem here. This basic space is blind to shape. You can add vectors together or stretch them out, but you cannot measure how long they are or the angle between them. To fix this, we introduce the inner product. It acts as our mathematical ruler and protractor, providing the structure needed to measure distance and rotation. We denote this operation with angle brackets around our two vectors, x and y. The most familiar version of this concept is the standard dot product in an n-dimensional space. You simply multiply the corresponding coordinate entries together and add them up to get a measurable value. To be a valid inner product, the operation must obey 4 strict algebraic rules. First, it has to distribute over addition. Second, you can pull scalars out of the first slot. Together, these form linearity. Third, it must have conjugate symmetry. And finally, it must satisfy positivity. When you work with complex numbers, conjugate symmetry is critical. The rule states that swapping the order of the vectors requires you to take the complex conjugate of the result. This guarantees that when you take the inner product of a vector with itself, the imaginary parts cancel out, leaving you with a strictly real, measurable length. As a side effect, pulling a scalar out of the second vector forces it to come out as a conjugate. If a mathematical operation passes those 4 specific tests, it is officially an inner product. Once an operation meets these criteria, the space gains a rigid geometric structure, allowing us to compute lengths and angles as if we were on a standard grid. This equation shows how we use the inner product to calculate exact distances. We call this the induced norm. We define length as the square root of a vector's inner product with itself. But we aren't restricted to the standard dot product. Here is a custom inner product in R2 that uses subtraction and different coefficients. At first glance, it isn't obvious that this satisfies the positivity rule. But if we plug the same vector in for both slots and simplify, it factors neatly into a sum of squares. Since squares of real numbers are always non-negative, and these only reach 0 if the vector itself is 0, the rule is satisfied. This animation illustrates how we push the abstraction into the space of square matrices. For these grids of numbers, we take the inner product by multiplying matrix A by the conjugate transpose of matrix B, and then taking the mathematical trace. We simply sum the elements along the main diagonal. This operation satisfies all 4 rules, allowing us to measure the distance between matrices. You can even construct a new inner product by mapping our vectors through an invertible matrix Q before applying the standard inner product. Because Q is non-singular, it preserves the distinctness of the vectors. It ensures that the only way a vector's self-inner product can hit 0 is if the vector itself is 0. This satisfies positivity, while the operation inherits linearity from the standard dot product. Length is not a fixed physical reality. It is a set of rules defined entirely by the specific inner product environment we choose to construct. This visual shows how we treat continuous functions as vectors. We translate the discrete dot product into a continuous form. Instead of adding up individual separate coordinates, we take the integral of the 2 functions multiplied together from 0 to 1. This integral executes the exact same mathematical logic as an infinite sum of multiplied corresponding points. Let's test this. Try applying the induced norm formula to the function f of t equals t. Pause the video here and see if you can calculate its length using the integral inner product. To find the length, we take the inner product of the function with itself, which means we integrate t squared from 0 to 1. The antiderivative is t cubed over 3. Evaluate that from 0 to 1, and we get 1/3. Finally, we take the square root. The length of the function t in this space is exactly 1 over the square root of 3. By treating abstract functions as vectors with measurable lengths, we bridge the gap between discrete linear algebra and continuous calculus. The exact same geometric rules govern both. This is the Cauchy-Schwarz inequality. It guarantees that the absolute value of an inner product is always less than or equal to the product of the individual vector lengths. Mathematically, this means the ratio between these values never exceeds 1, forcing the result into the valid range for a cosine function. This is the bridge that allows us to define a consistent angle between objects as abstract as matrices or sound waves. From Cauchy-Schwarz, we derive the triangle inequality. This proves the geometric truth that the shortest path between 2 points is a straight line. Vector x plus vector y is always shorter than or equal to the lengths of x and y traveled separately. This law holds true even in a space made of infinite dimensional functions. Inner products grant geometry to algebra. Any operation that passes our 4 strict rules is valid. Establishing this framework is how we identify perpendicularity and distance inside abstract data. If you found this breakdown helpful, like this video and subscribe to the channel for more guides through classic mathematical texts like Hoffman and Kunze. The inner product acts as a mathematical translator. It takes an unshaped void of numbers and applies strict structural rules, turning it into a measurable universe.